Okay, I wanted to talk a little bit about some really quite useful tools that we use in physics for those things that we discussed last week about direction and magnitude. So, in other words, things like distance and speed, where we don't care about the direction, just the magnitude. Magnitude is basically just a big word for size. And things where we do care about direction, like displacement, velocity, and acceleration, and a number of other things that we'll discuss as we go along. So we have these tools called vectors, which help us to represent those, and we'll spend a bit of time playing with those and using them. I have to admit that after having done this for a very long time, I tend to think in vectors. So if I'm walking along a rocky beach, I'll be kind of mentally imagining little force vectors as I step on a rock to see whether it's going to slip out from under me or not. Now that might be, again, slightly weird and nerdy, but I just find them really useful thinking tools to think about what's going on in a particular situation. So physics, we describe things qualitatively and quantitatively. We certainly talk about the qualities of things. So this particular vehicle is very slippery, very aerodynamic. Now we could quantitatively describe that as well. We have a coefficient of drag as a number. So we could say this vehicle is very slippery. It has a CD, coefficient of drag, of 0.32. So that's a quantitative description, but we could also just say a qualitative description. This vehicle is much more slippery, much less draggy than this vehicle over here. So qualitative and quantitative language. Scalar quantities, we can measure them quantitatively, but we don't require any other information than just a number. So, for example, the mass of a chocolate bar, 200 grams. So we've described it. We don't need a direction. It's not a chocolate bar that is 200 grams northwest or 200 grams downward. There might be a weight force associated with it that's downward, but the actual mass isn't a vector quantity, it's a scalar quantity. We could also describe the chocolate qualitatively. We could say it's yummy, we could say it's brown, we could say it's relatively soft depending on the temperature, we could say it smells good, and so on. So there's qualitative descriptions we could use. The quantitative description, and I mentioned that distance and speed are scalar quantities. A scalar, we just need a number to define. Vector quantities, we want to know the direction and the size, the magnitude. So forces, we want to know how strong it is, but we want to know where it is as well. And that will become more important when we go, okay, there are two forces acting on this object. Are they acting against each other and balancing each other out so nothing happens, or are they acting with each other and accelerating the thing faster? If we don't know the direction, we can't answer that question. So the direction is really important. So we might say the force of gravity on my keyboard is 10 newtons downward, because it's about a kilogram, something like that. So to completely describe a force, which is a vector quantity, we need both a number for the magnitude, 10 newtons, and a direction, downward in this case, for the gravitational force acting on an object. Velocity is a vector, and I mentioned that. It's a quality that we care about the direction. Speed is a scalar. I'm probably belaboring the point at this point. So velocity and speed, the difference, and scalar and vector. But it's a nice example to keep in your head, I guess. And distance and displacement as well. So displacement, velocity, force, acceleration are all vector quantities, and there's a number of others that you'll learn about as we go along. But really realizing this tool of vectors, and what we tend to do is represent them as an arrow, where we use the metaphor that the length of the arrow represents the magnitude of the quantity. So a small force will have a little arrow, a big force will have a big arrow, and those will be actually drawn to scale. So if it's 2 newtons, it will be 2 units long. If it's 10 newtons, it will be 10 units long. So drawing them that way allows us to actually solve them graphically, and I'll do a video about solving vector sums, vector equations graphically, just drawing it on graph paper, making it really clear, careful to scale, and using that to calculate it. Or we can also use a little bit of maths and a little bit of trigonometry to solve them. So we'll talk about how we actually add up vectors, subtract vectors, use vectors in various ways. this is a concept that some students find quite difficult. I tend to find, I've taught a fair bit of chemistry as well, students really struggle with the mole concept in chemistry, and they struggle with dynamic equilibrium in chemistry. Students tend to struggle with vectors in motion, but it's really not that difficult, I hope. I hope to demonstrate to you that it's actually not that difficult if you have a physical sense of what's going on and then use the tool to describe that. In other words, you don't get obsessed with the tool, you use the tool to represent your knowledge of physics.